In the last lesson, we learned about what a horizontal compression is. We represent that with the letter K. You may have wondered why we use the letter K for a horizontal compression when we've already learned that K is supposed to be part of our vertex when we're talking about vertex form of an equation. That's because from here on out, we're going to use different letters to represent transformations. We can still talk about A, H, and K for a vertex form. That's fine. But you have to understand that when I go on, maybe just to give a quick preview, we're going to actually replace K with C for transformations in the future, and we're going to replace H with D. A is still going to be A, and K is going to be K, as we learned last lesson, but we are going to replace a few letters. But I'll get to that when it becomes important. So, talking about transformations, you learned in grade 10 how to describe transformations based on A, H, and K. And looking at, now here's the graphs of them. This is our parent function, y equals x squared. This is our transformed graph, y equals negative 2 x minus 4 squared plus 1. Although I'm not going to worry about really looking at that graph right now. Let's just start by looking at the equation. So if we got this equation, again, we should be able to tell just from the equation what the transformations are. So A is negative 1, so let's start with that. Sorry, negative 2. A is negative 2. What do I want? A equals negative 2. So I'm just going to put that there. So what does the A equals negative 2 tell us? Well, it tells us that it's reflected in the y-axis. No, sorry, the x-axis. Vertical reflection. So that's what the negative part tells me. And the 2 part tells me that it's vertically stretched by 2. So to vertically stretch something, I could take all my y values on my original function and multiply them by 2, and now they're twice as big. We can see that h is positive 4. Remember, it's positive 4 because when I pull it out of the equation up here, I change the sign. And that's my horizontal shift. And in fact, maybe rather than writing horizontal shift, I'll just say shift right 4. So if h is positive 4, it's going to go to the right. If h was negative 4, when I took it out, it would go to the left. And K is supposed to be, this should be a plus, an equal sign. K equals 1, which means you're going to shift up 1. And we have to do these things in order. The order that I mentioned them, the reflection, it doesn't matter, the reflection and the vertical stretch we can do simultaneously, but I have to do the stretching, I have to do the A value first, and then I have to do my shifts. So if we were just to look at this graph before we see the stretched one, so on the right-hand side of the screen, imagine reflecting that parabola down, so it's reflected downward, okay? So that's the first thing I want to do. Then I want to think about stretching it, so it's reflected and stretched, so every point's going to become, every y value, in addition to being opening down, it's going to go twice as far downward. It's going to become stretched out vertically. And then I'm going to take this whole thing and I'm going to shift it 4 units to the right, which you can see has happened, and we're going to shift it up 1 unit. And so you can see that this red one that I've sketched is the same shape as the one that's the final graph. And if I just move it a little bit to the right and up, then I've got my transformation. So that's how transformations work, what you should know up till now. But we can apply these same transformations to any relation. We can also apply a horizontal stretch compression that we looked at in our previous class. So the following is transformations in function notation. So instead of having our basic function just be y equals x squared, as we saw in the last class, we're going to let y equals f at x be our parent function. Okay? So that's just to represent that it can be any function. So, again, depending on where we find our different numbers, we're obviously not going to see the actual letters a, k, d, or c in a function. We're going to see numbers there, and we're going to tell if they're a values depending on where they are. A is going to be found right after the equal sign before anything happens, not inside brackets ever. K is always going to be found inside the function, whatever the function is. So if it's quadratic, it's going to be inside brackets. If it's a radical function, the square root one, it's going to be found under the square root sign. If it's a reciprocal function, 1 over x, it's going to be found in the denominator, right there near the x. So it's always found inside the function, so to speak. So that's how we can tell which is a and which is k, by where they are. D, just like K, D is what we're now calling h, right, from what we used to call h in vertex form. And we'll still call it h in vertex form, but when we're talking about any function now, we're going to call it d. And it's the same thing. It's inside the function, as you can see. So it's inside the brackets. And it's going to be it's going to be plus or minus something from the x. But it has to be inside brackets. That's your tip-off that's a d value. Because if it's not inside brackets, then it's a c value. And that's our vertical shift. Remember, and for D, just like H, we always change the sign when we pull it out of an equation. So here's an example. We've got, this is an A value. I can tell because it comes right after the equal sign, which means that it's going to reflect it in the x-axis, and it's going to be vertically stretched by a factor of 2. This is a K value because it's inside the function, but it's in front of the x, right? K values are in front of the x, D values are inside the function, but they come after. So this is my K value, and we learned last class that a K value of 3 actually does the opposite of what we might expect. It doesn't make it 3 times wider, it makes it 1/3 as wide. D is my horizontal shift, and I change the sign when I pull it out of the equation, so this one would be shift 4 to the right. And this C value that comes at the very end, it's not inside any brackets. That's just my vertical shift, my C value, it's up by 5. Notice that both the horizontal compression and the horizontal shift are opposite of what they should appear to be. In other words, until you get really familiar with this, you might originally think that, okay, a K value of 3 should make it 3 times as wide, but it actually makes it 1/3 as wide. And you might think that this -4 inside the bracket should move it 4 units to the left, but because we change the sign, it moves it 4 units to the right. That's all I mean by that they're the opposite of what they appear they should be. So let's just practice this, state a few transformations. So we can transform individual points. So we've got these points here that we want to transform, right? We can have a whole function like this quadratic here, but I don't have to transform the whole function. I could just transform this single point. I could reflect this point in the x-axis, I could reflect it in the y-axis, I could move it closer to the x-axis, I could shift it up or down, I could shift it left or right. So I can do a single point. I don't have to do an entire graph. And that's all this is about. It's just taking one point and applying transformations. So if my function is this single point, in each of these cases, these are my f at x's, this is my function, then y equals 3f at x means I have to transform it. So I have to identify what these different values are. Well, based on the fact that this 3 comes right after the equal sign, not inside the function, it has to be an a value. So I can tell that this 3 must be a vertical stretch. So if this is a vertical stretch, that means I'm going to take the point 1, 2, and I'm going to multiply the y value by a, right? And so I'll get the new point 1, 6. That's the new transformed function. This is my answer, in other words. All I've done is I've transformed that point by stretching it by 3, right? We know that this a value of 3 stretches by 3. And well, if I started at 1, 2, clearly the point 1, 6 is 3 times higher. That's what this is telling us. For the second one, judging on where this value is here, it's not inside the function. Inside the function would be inside the brackets. It's not right after the equal sign either. This is a C value. This is something that comes at the end. That's a vertical shift. Vertical shifts affect the y-axis, don't they? So if I take 5, 3, and it's a vertical shift, I'm going to, in this case it's minus 5, I'm going to move the y value down by 5, so I subtract 5. So my new point would be 5, -2. And again, compare this 5, 3 and 5, -2. They're exactly the same, except we've shifted the point down, vertically down by 5 points. In this next example, now we're inside the brackets, aren't we? But it's after the x, which makes it a d value, which makes it a horizontal shift. And remember, we changed the sign. This becomes a positive 3. And so if it's a horizontal shift, we're going to take our original point of -4, our x-coordinate, and we're going to add 3 to it because it's horizontal, and so we do that to the x-coordinate. So it becomes -4 plus 3. It doesn't affect the y-coordinate. And so I end up with -1, 6. And again, let's think, does this make sense? Well, I started with -4, 6, and I shifted 3 to the right, and I got -1, 6. So yeah, that makes sense to me. In the last example, the only thing we haven't done yet is a k value, and this is definitely a k value because it occurs inside the function, inside the brackets, but this is in front of the x, so it's times x. So in this case, I'm going to start with -8, 1, and we've seen for k values, we divide by the k value. It's going to make it half as wide in this case because k equals 2. So I end up with a -4, 1. And again, let's compare them. -8, 1 cut in half horizontally becomes -4, 1. It gets twice as close to the y-axis, it's half as wide. If we put all this together, you may remember from yesterday's lesson, I just did x over k and then just, that was it, and then y. Well, if we add all these transformations, it's going to be xy becomes x over k plus, I'm not sure why it's plus or minus, I'm going to get rid of these minus signs. It's just going to be x over k plus d and ay plus c. And let's see how we can put all this together. So again, as I said, we can have a function that's just a bunch of points. So in this case, we got 3 points. So in this example, the function f at x was just a single point each time. It was 1, 2, it was 3, 5, 3, it was -4, 6, whatever, at a time. But this time, f at x is all 3 of these points. So 4, 1, 8, 2, 12, 3. So that's the entire function. It's just those 3 points. Now let's transform those 3 points. So again, it's all about identifying what do we have. Do we have a, do we have k, do we have d, do we have c? And then doing what we need to do. So this one is an a value because of where it comes from. It's right in front of the function, so that means I've got a vertical stretch, I've got a reflection in the x-axis, and I've got an a value of -2. So a reflection in the x-axis and vertical stretch by 2. So if I just take this set of points, I am going to multiply all my y values by -2. Why am I multiplying just my y values by -2? Because a is a vertical stretch. It only affects the y values, and it's just straight multiplication. So I have x value stays the same of 4, but 1 times -2 becomes -2. For the next one, the x-coordinate stays the same at 8, but 2 times -2 becomes -4. And then for the last one, 12 stays the same because that's my x value, but 3 times -2 becomes -6. So all my y values were reflected in the x-axis by multiplying by the negative, and they were stretched out twice as wide. Okay, what's going on in B part? Well, I see two things going on at once. I see that there's a D value of 2, and there's a C value of 3. Again, I can tell what they are by where they are. Keep referring back to this formula here. This formula is going to tell you, remind you of where you find the different values of A, K, D, or C. There we go. It's going to put that in a box. All right, so back to this one. We're starting with the point 4, 1. So if I have 4, 1, the D value is a horizontal shift. So I'm going to do 4 plus 2. I'm going to show a couple steps for this one. So 4 plus 2, and 1 plus 3. I am adding the D value of 2 and the C value of 3. And let's just do it, tidy it up underneath here. 4 plus 2 is 6. 1 plus 3 is 4. There's my new point. So 4, 1 became 6, 4. And then for the next one, 8, 2, I'm going to do 8 plus 2 and 2 plus 3. Again, my D value and my C value, I just add those on there, and I've got the point 10, 5. And then my last one, which was 12, 3, I'm going to do 12 plus 2 and 3 plus 3, again because of my D value and C value respectively. And when I simplify that, I get the point 14, 6. So there's my new transformed point. Let's put a nice little circle around it to show that we're done. All right, there's my transformed point. Okay, here we've got a doozy because we've got an A value of -2. Not -1, -2. We've got a K value of +2. We've got a D value of -1, changing that sign when I take it out. I've got a C value of +5. So I'm going to go back to this mapping formula. This mapping formula is going to become your friend. All it's saying is take your x coordinate, divide it by k, and add d. Take your y coordinate, multiply it by a, and add c. And so for the first two examples, I didn't have to do all 4 of them. For the first example, I only had to do the A part. For the second example, I only had to do the D and C part. But this one, I need to do all 4 of them. But I'm still starting out with the same 4, 1, 8, 2, and 12, 3. So let's just show our work here. So 4, 1, so I'm going to do 4 divided by k, which is 2, plus d, which is -1. I'll just write -1 rather than plus -1. And my A value is -2 times the k times the original value of 1. I'll highlight in a second to make it clearer, plus 5. So where did all these numbers come from? Let's use yellow for A. So -2, that my A value affects the Y. I'll use green for K. I divide by K. I'll use blue for D. And I will use pink for C. So again, that's just going back to this formula here. A, K, D, C. So I'm just following that formula up above and doing these operations. So when I simplify it, 4 divided by 2 is 2. 2 minus 1 is 1, so my new x value is 1. -2 times 1 is -2, plus 5 is 3, and that's my new y value. And I do that point by point. So for the next point, it would be 8 over 2 minus 1, and 2 over 2, sorry, not 2 over 2, and -2 times 2 plus 5. Again, where those numbers come from, I'm using the exact same A, K, D, and C values that came from the formula, right? So the highlighting shows you where they came from. It reminds you. 8 divided by 2 is 4. 4 minus 1 is 3. So my new x coordinate becomes 3. -2 times 2 is -4. Negative 4 plus 5 is 1. And again, so now I've just got this new point with all these transformations done to it. I got the new point. If I do it one more time, because I have one more point, I'd start with 12 over 2 minus 1, and I'd have negative 2 times 3 plus 5. Let's highlight one more time just to show where they came from, to remind you where all these numbers came from. Then I simplify. 12 divided by 2 is 6. 6 minus 1 is 5. All right, so I got my new x value from doing this. And negative 2 times 3 is 6. Negative 6 plus 5 is negative 1, so that's my new y value. And this becomes my answer once I've done all of them. So I can do any one of these transformations. I can do a couple of them like I did in B part. I could do all 4 of them like I did in C part. But I'm always following this pattern that I've highlighted in this box right here. I call that the mapping formula. Okay, so the last example involves just doing some transformations based only on graphs. So instead of giving me a list of points, here's a picture of a graph. We recognize this as an absolute value graph, right? It's the parent function one. In fact, here is the equation of it. So we know at this point that we can tell what transformation we have by looking at the where the value is found. So if f at x equals the absolute value of x, this 3 is in the a spot right after the equal sign. What does a do? It multiplies, it makes our graph 3 times as tall. So in other words, I'm going to take all my y values and make them 3 times as tall. So 0, 0 is going to become 3 times as tall. Well, my y, 0 times 3 is still 0. But this point, let's say here, that was 1, 1. I'm going to multiply my y value by 3, and I'm going to get 1, 3 to make that point, that 1 point, 3 times as tall. And then this point here, that was 2, 2. I'm going to multiply the y value by 3 to make it 3 times as tall. Picking up what I'm saying here? Every point, the y values, the x values will stay the same, and the y values will get 3 times as tall. So this point 3, 3 would go up to 3, 9. Likewise, negative 1, 1 would go up to negative 1, 3, and negative 2, 2 would go up to negative 2, 6, and negative 3, 3 would go up to negative 3, 9. And so we get this graph that is 3 times as tall. Everything else about it stayed the same because the only transformation in this case was to make it a vertical stretch. And by the way, what 3f at x would be, if I was to write it as an equation without, to rewrite it, I'd write it as 3 absolute value x. So again, the 3 is outside the absolute value sign. It's outside the function. That's what makes it a vertical stretch. If the 3 had been inside, it would have suddenly become a horizontal compression. Okay, for this one, we're starting with the parent function of a reciprocal. And so, again, if I want to rewrite this, maybe I'll rewrite it first. That would be the same as to put this into one equation, would be 1 over x plus 3 with a minus 2 on the end. The plus 3 is inside the function. That's my d value. I can see that my d value, again, when I take it out, I change the sign, it becomes negative 3. This negative 2 at the end is clearly a c value that's, it's not inside the function, so that's negative 2. So what is this telling me to do? Remember, d values are horizontal shifts. So a d value of negative 3 says move 3 to the left. Take each point and move 3 to the left. A c value of negative 2 is a vertical shift. It's saying take every point and move it down 2. So in the interest of time, let's just sort of do this one point at a time and see what we get. Let's start with this point. If I move it 3 to the left, I get over to negative 2, and then down 2 takes me to, actually, maybe I won't start with that one because I don't want to end up on one where I already am. Let's start with the ones down here on the left. Okay, let's start with this one. This is probably an easier one based on the way it moves. No. Yes, sorry. I'm just trying to decide which one is best to start with. Let's start with this one. It's an easy one to read. -1, -1. So I'm going to move 3 to the left and down 2. So I've got this new point at -4, -3, because it moved 3 to the left and down 2. This point, which is halfway in between, so about -0.5, -2, if I go 3 to the left, it's going to go over to here and then down 2, so about here, right? Again, I'll get rid of all this extra stuff, but it's going to end up down here. The shape isn't going to change. It's going to stay exactly the same. It's just being shifted to the left or to the right. So this point going 3 to the left takes me over 1, 2, 3 to here, and then down 2 would take me down to about there. So you can see how the shape is moving. And in fact, I can probably draw my curve at this point. Even we can think about the horizontal shifts are going to affect the asymptote. Remember, we have a horizontal asymptote and a vertical asymptote, and maybe that would have been a good thing to start with. They're going to shift as well. They're going to shift 3 to the left and down 2. So if I take the x and y axis and shift them 3 to the left, that means my new vertical asymptote would be here at -3, moving that vertical asymptote 3 to the left, and then the horizontal asymptote, if I move it down 2, so my asymptote is moving as well. So that'll help me draw my sketch better. So I probably could have done that first, but anyway, there we go. Now if I move all these other points, move this one 3 to the left and down 2, then I get a point here. If I move this one 3 to the left and down 2, I get a point here. If I move this one 3 to the left and down 2, I get a point about here. If I move this one 3 to the left and down 2, I get a point about here. And you can see what's happening. Again, it's just curving near the asymptote. Okay, for this one, we got a square root function. So a is a half. D is +3. And again, this 3 is inside the function. If I was to rewrite this function with the transformations, I write it as y equals 1/2 square root x minus 3. That's putting the whole thing together like this. So anyway, there's our parent function. We're going to make it half as tall and move it 3 to the right. So let's do this one a little faster since we've done a few before. So if I take this point, make it half as tall, 3 to the right, then that point there becomes this point. Let's just use different colors. This point, half as tall and 3 to the right, would be here. This point, half as tall and 3 to the right, well, that's off my graph, but it's going to be somewhere over here, isn't it? Let's do another point. Let's do purple. What if I took this point, made it half as tall, and then 3 to the right? Well, I'd get a point here. What about the one that's 0, 0? Well, if I take that one, what else have I not used? Let's use blue. So this point, half as tall, half of 0 is still 0, but then move it 3. Did I only move it 2 to the right? I moved some of these only 2 to the right. My mistake. Let me move it 3 to the right. Half as tall and 3 to the right should have been here and here. Sorry, not there. Here. So back to this blue one at the origin. Half as tall is still on the x-axis, but 3 to the right moves it over to here. So the shape is the same, although it's been vertically compressed, and it's been moved 3 units to the right. In this last example, we've got an a value of -1. So it's reflected in the x-axis. We've got a k value of 2, so it's compressed horizontally, and we've got a c value of 4, so it's going to be shifted up 4. This might be a good one to work on point by point. So let's start with the origin. So 0, 0, if I want to transform that, I'm going to do 0 divided by 2. There's no d value, so there's no horizontal shift. And I'm going to do 0, -1 times 0 plus 4. So I'm using the mapping formula again. So 0 divided by 2 is still 0, and negative 1 times 0 is 0, but plus 4 is 4. So that one point, the origin point, moves up to here. So the vertex is now at 0, 4. Let's take this point here. So this is the point negative 1, positive 1. And so if I map that one, it's going to be negative 1 divided by the k value of 2. It's going to be the a value of negative 1 times the x-coordinate, the y-coordinate of positive 1. And I'm going to add 4 to that. And so that's going to equal negative 0.5, negative a half, and the x-coordinate becomes positive 3. So I get a new coordinate for this one at negative 0.5, positive 3. So interesting. But that's part of the reflection that's going on, right? So now the parabola is opening down because the a value is negative. Let's take this one, do this one in purple. And so it's the point 1, 1. And if I map that one, it's going to be 1 divided by k. It's going to be negative 1 times the y value plus 4. So that gives me 0.5 and positive 3. So again, I get a point here. So it looks like my parabola is going downward, as I already saw. And again, once I get an idea of what's going on, I can sort of follow a pattern, right? I don't need to do every point. I know what opens down. So what's happening? It's opening down. I've already taken care of the a value. They're all going to open down. But from the vertex, it's going to open down, and it's going to be compressed half as wide and moved up 4. So this point here, what color haven't I used? This point here. So if I take this point, which is 2, 4, it's now going to be 1. It's going to move over. It's going to be half as wide. So it's going to move over to 1. And then it's going to be reflected downwards. So it's going to go down to negative 4. But then it's going to be shifted back up 4. And I'll get this point at 1, 0. And since it's symmetrical, once I got one of them, I know I can get the other one. And that's enough to draw on my sketch. So this one got a bit messy. Sometimes it does. When you show your work this way, it gets kind of messy. I'm going to show you a way of doing it without doing it such a sort of a messy way in a later lecture, or next lecture probably. But for now, all you need to do is figure out what A, K, D, and C are and show your work, whatever way makes most sense for you, for starters, because the purpose of this lesson is just getting familiar with the different transformations.